Hi everyone, we are Fillippo Calcerano and she's Letizia Martinelli, and we are researchers of the Institute of Heritage Science of the National Research Council of Italy. That is one of the major national and international players in heritage science. And the Built Heritage Innovation Lab to which we belong is coordinated by Elena Gigliarelli and is one of the ISPC laboratories. Whose main areas of intervention are heritage diagnostics and protection, conservation process knowledge management on heritage BIM platforms, energy and environmental improvement, and exhibit, museum, and archaeological site design. And this is our current staff, composed mainly of architects and engineers. In this presentation, we will be looking at built heritage improvement from an energy and environmental point of view, and with the support of digital technologies, up to seeing what we have actually done on one of our case study. That it is about a research project we are finishing at the moment. Yeah. So first things first, cultural heritage plays a key role in many of the 17 objectives of the Sustainable Development Goals agenda, and it can be considered as the fourth dimension of sustainable development, along with the economic, environmental, and social ones. This central role is supported by a number of other reports and entities. And obviously, energy consumption and climate change are an issue also for the built heritage sector. An issue in terms of risk assessment from the impacts of climate change, but also in terms of reduced usage of buildings, which is the most important factor to ensure their conservation. Historical buildings are not the most numerous nor energy-intensive sector of the building industry, and they generally behave more efficiently than buildings constructed between the World War II and the 80s, thanks to their passive behavior optimized for their climate. However, climate change is weakening this assumption by undermining their natural functioning, with significant consequences for their conservation as well. From this point of view, it will be necessary to develop increasingly advanced methods of adaptation to climate change in order to enhance their resilience. In addition to vulnerability to climate change, the issue of energy consumption now and in the future needs to be also addressed, both from a conservation valorization perspective to avoid fuel poverty and thus building abandonment, and from a sustainable development perspective, reduce consumption and emission, help mitigate the causes of climate change in the long run. How to do so? Well, despite the EU being an early mover on the climate change adaptation and mitigation policies, and having strongly committed on energy efficiency of the construction sector, coordinated action on the built heritage is still lacking. It is no coincidence that the Climate Heritage Network, possibly one of the most important network of actors of cultural heritage from an environmental point of view, released its European Heritage Green Paper to assess the role that heritage has or should have in relation to the European Green Deal. That is not very sensitive to the potential of cultural heritage in the fight against climate change. The potential for this type of studies, however, is very high, especially in Europe, with a flourishing of research projects on this integration, historically mainly articulated in the direction of risk assessment and more recently also in terms of adaptation and mitigation. The Italian debate, in the wake of what has happened in the structural analysis field, today uses the formulation of improvement for the energy and environmental intervention on built heritage as a valorization and protection strategy, however subordinate to their conservation. The approach involves compliance with the guiding principle of international restoration charters that are minimum intervention, reversibility, distinguishability, physical, chemical, and figurative compatibility, and the respect for the material and figurative authenticity of the asset. And the study of built heritage from an environmental design perspective also guarantees at least 4 fundamental advantages: disciplinary cross-fertilization, added value of knowledge, understanding of building know-how optimized for the reference climate is useful in terms of design and diagnostics, beacon for the sector, and technological stress test. For the first, the connection between cultural heritage and the environment, probably already anticipated by John Ruskin, was already present in the UNESCO Convention of 1972. We are in 2022, so it's been 50 years from this convention, and became even more explicit with the 1994 Aalborg Charter. Environmental design and conservation have always had many methodological aspects in common, from the transgenerational temporal perspective to the need to deal with strongly interdisciplinary, holistic, and multiscalar approaches, to the need to move in a space of uncertainty on the border between hard science and humanities, which provides us possibly with the most interesting insights. For example, from the conservation theory, where scholars argue that the division between cultural and technical aspects does not exist and that the building must be studied as a complex system that cannot be analyzed by parts, thus allowing us to have a compass, a guide for the introduction of innovative technologies and methodologies on historical buildings. In other words, using deterministic approaches on heterogeneous buildings with high levels of uncertainties should nevertheless be included in the science reasoning process to pursue the best possible rational formulation of a problem on the basis of data, hypothesis, and interpretation. Another aspects concern the nature of historical buildings that, being optimized for their climate, are an inexhaustible source of ideas for environmentally and energetically conscious buildings. Not to mention that the study of the bioclimatic behavior of historical structures provides an added value of knowledge, thanks to the possibility of reconstructing their natural functioning processes while enhancing their distinctive characteristics and identities linked to the local microclimate, that can be used both for the energy efficiency and for conservation, because, for example, sun and wind strongly affects also decay processes. The third aspect concerns the European Directive 2010/31, which emphasizes the role of public administration as an example in the energy efficiency of the construction sector. Historical buildings as symbols of European cities, if not of Europe itself, reinforce this role, as also underlined by European research projects on the subject like Securba or BIP that we will be also showing you today. Finally, the complexities related to those interventions, of which we will have a taste later with Letizia, makes historical buildings the most demanding experimental laboratory ever to test new technologies, approaches, and their scalability. So that's why we talk about the stress test. And now on to the technologies that we believe are key right now to support built heritage, energy and environmental improvement intervention.
Hi everybody, I continue along with the discussion of Fillippo, and especially we will be talking about two of this technology. The first, that is building performance simulation, and then the second, that is building information modeling, the way they can be applied for the energy and environmental improvement of buildings, and also the way they can interact with each other. Simulation-based design is based on the definition of a model of a building that can represent his behavior, and it relies on a simplification of the physical entities of the real world that are modeled up to a certain level of abstraction. And simulations are extremely promising in the field of built heritage, because they allow us to understand and analyze complex phenomena, and they are also have the possibility to ensure feedback on the effect of interventions on the building, not also on the effect of intervention on the energy efficiency of buildings and on comfort, but also on the effect on the conservation of the building, for example, on decay phenomena. As Fillippo was saying before, many passive elements of the environment, wind and sun, for example, have a very strong effect on decay patterns that can be taken into account in a holistic approach. However, even if they have such great potentials, these tools for simulation-based design are not very well spread inside the architectural and engineering field. They are not used in the early stages of design processes, and especially they are not used for historical buildings. And the very few applications that they already have are concentrated in Italy. The reason why there is such a lack of studies on the topic can be linked to the complexities of historical buildings that is in contrast with the simplification that are needed for energy and environmental modeling. For example, historical buildings are characterized by complex geometries that are very difficult to deal with for simulation software, that struggle with, for example, correctly representing the relationship between surfaces. Then there is a lack of standardization and a lack of homogeneity within historical constructive system, that is also in contrast with the need for simplification within simulation processes. There is a great importance of massive behavior for historical buildings, especially buildings that are built on with masonry, and many calculation methods of simulation software are limited in the representation of wall thicknesses when it goes beyond a certain amount. So this requires very specific countermeasurement and attention to represent this type of conditions. And similarly, there is a great importance of moisture transport for masonry building that have a very hygroscopic nature and behavior that is not typical for new construction, so it's not well taken into account by simulation software. And finally, as I was saying before, there is also in general a lack of use of these tools in the architectural and engineering professional practice, and there is also not a great understanding and common knowledge framework among different experts in the field. BIM is the other technology that could be that have very great potential for the energy and environmental improvement of historical buildings. And the definition of a BIM, of a building information model, is the digital representation of the physical and functional characteristic of a built asset. In general, a BIM is a model of the building that associates the 3D representation of the building elements to their characteristics represented as data. For example, a wall in a normal 3D modeling software is just it's just a shape, just a box, while in a BIM software, a wall is represented also not only by its shape, but also by its stratigraphy, by its material, by a series of data associated to it, for example, his date of construction, and also is represented by the relationship that the walls has with other objects. For example, a windows is associated to a wall, and they have a given relationship, like the windows is considered as a part of the wall. And this capability of representing a simulation, an idea of the building, and also this capability of acting as a building database is very important within built heritage, because built heritage conservation practices are based on multidisciplinary decision-making processes, which require the structured organization of historical, diagnostics, and document information. Therefore, a BIM process that is applied to historical buildings, generally known as heritage BIM, so HBIM, can combine inside a centralized system the management and production of information on the building associated with this 3D representation, so very easy to understand, that can ensure the permanence, consultation, and implementation of data that can be accessible and usable by experts from different disciplines. Many type of procedures can be integrated within an HBIM methodology. For example, design and maintenance activities, the management of information, simulations, geometric surveys, or also multidisciplinary analysis. And therefore, BIM could be used for an energy and environmental improvement process, both for its possibility to be used as an information system, so a collection of all the data on the building that are relevant for energy and environmental simulations, and also because as BIM represent the behavior of the building and the connection between the building parts, it is already can be considered a simulation of the building. So, given then an HBIM model and a simulation model share a lot of information, because they both contain information on the building, thermal, energetical characteristics, and so on. For example, both contain information on the envelope stratigraphy. The possibility to share data among these two environments could save time and reduce costs. However, the integration, so the interoperability between the BIM environment and simulation is still very complex and under development. And the two most used open file schemes for this type of interoperability, IFC and GBXML, still lack the possibility for very efficient transfer of data, and they required a lot of manual check and post-processing of the data, because they are very much prone to error. And this is a general problem, and again, as we were saying before, it depends on the simplification assumptions of the energy modeling, and also the need for a very specific data conversion, because the representation of data between a BIM model, that is a 3D model, and the representation of data in a simulation model are very different. And is also very much worse for the representation of built heritage, because as we were saying before, built heritage has its own issues, both for its representation in BIM and for its representation with building performance simulation software. And again, the interoperability issues that are more commonly reported in the literature concern geometric issues that can be of a lot of types, problems with the definition of space boundaries, incorrect representation of geometry, incorrect representation of spatial hierarchies and nested elements, problems in the normal surfaces, and so on. And also a problem in the shared of alphanumeric data. Data could not be exported well by the BIM software, could not be imported well in the building performance simulation software, or they can be imported but with errors, or they can be not imported at all. Therefore, up to date, there is no possibility for a complete error-free automated interoperability process, so exporting from the BIM software to the BPS software. But there is the need for semi-automatic approaches that, thanks to the possibility of human intervention to check on the data, to manually tweak the data, to ensure its transfer, are more reliable than fully automated processes. But this type of semi-automated process and the need to streamline the transfer of data as much as possible in these early stages of this kind of development needs a preliminary feasibility studies on the BIM to BPS process that has to involve all the experts that are part of the process. So the simulation expert, the conservation expert, the BIM expert, and the expert on common data environment, that is the expert of data transfer. And these preliminary feasibility studies should help these experts, so within this multidisciplinary process, define a shared knowledge framework, map the data that has to be transferred between the two environments and the strategy to make this data transfer, and perform a series of interoperability tests, from very simplified transfer of data with very simplified models with the definition of way more complex tests up to the final transfer of data from the final model of the complex case study. And this process, so this preliminary analysis and study on finding all the possible errors and all the possible problems of the process in order to streamline it to the final application of a real case study, is also very important to keep each expert in his comfort zone, and so to have a process that is as simple as possible and is flexible and scalable to be also applied to the market. Because if a process that is developed for interoperability is very complex, can be applied also inside a research institute, then it will never be used in the practice. While our aim is to make this type of approaches as useful as possible for the general sector. This workflow that I described to you is the workflow that we normally apply to our case studies, and you will see an application later on. And so, as I was saying, it involves the collection of as much data on the building as possible, geometric data, but also energy and environmental data from analysis, field analysis, that will be collected and integrated inside the HBIM platform. There is an HBIM model, but also a general common data environment that include all the data that can be integrated directly in the model. Then there is this interoperability process. Therefore, this export of the HBIM model within a simulation software and the simulation of the current conditions of the building to calibrate and validate the model itself. Then, parallel to this process, design a solution for the energy and environmental improvements of the building are developed, and they also are simulated, taking into account their costs and time. These simulated design solutions are collected inside design scenarios, and in order to make the process feasible and really applicable to the building, they need to be integrated with also a funding process to find the money to do the renovations. And a way that is we apply to fund this funding resources is through energy performance contracts. And more information on the process that we applied to BIP project, that is the one that Fillippo is gonna show you in a moment, can also be found in a guideline on the process that we publish on Zenoto. That is an open access platform financed by the European Union.
Yeah, so you have seen it behind the lines, this BIP name. So finally, you will get to know what we were talking about. And the last part of the presentation is to briefly show you how this holistic and digital approach was applied to an Italian case study, a case study of the BIP project, any EE-HBIM MED project. And Palazzo Maffei Borghese, our case study, is located on Via del Clementino in Rome, in the Campo Marzio historical district. It has a floor area of about 3,500 square meters on 4 floors plus an underground basement, and its construction started in the second half of the 16th century. Despite pre-planning activity actually went really smoothly, despite also COVID-19 crisis and all the related logistic problems. We also had a great collaboration from the occupants, from the technical management, from the staff in collecting all the documentation. But still, it was really a challenging process to gather this documentation, because it was held by different administrative bodies, and we had to cope with that. For example, we received the data on the last restoration containing a lot of useful information only after being forced to develop a series of additional analyses due to the lack of this specific information. So this was really it's really important to plan ahead and to be ready to to tweak your process if you are not able to get the material in due time. And that's what we actually had to do in some cases. About the historical analysis, although there were no specific in-depth studies on our case study, the presence of Palazzo Firenze in the same urban block was really useful, because on Palazzo Firenze we had some book to look, we had some documentation, and was really helpful. And also the position in the historic urban fabric of Rome city center that was subject to a lot of studies during the centuries also helped a lot. Also, thanks to the cartography and typological studies of coeval buildings in the same area that you can see in the slides, in order to start to indirectly reconstruct the main transformation of the building, its construction techniques and its materials. So we started with some ideas based on what we had all around us. And yeah, the geometric survey was performed integrating both terrestrial laser scanner and simultaneous localization and mapping laser scanner technique that you can see in the small video that is going. Yeah, obviously point cloud was really important to get the overall geometric representation of the building, also due to the lack of consistent drawings and the fact that it was really big and complex. But however, the critical and graphical notes from the field survey of the team, in the picture you see Letizia doing stuff, was really important. The drawing was really important because we needed it to understand some architectural and key elements to be represented that mainly were not thoroughly addressed by our survey techniques. For example, windows that needed a lot of really precise measurements and analysis to be modeled for the simulation purposes. Conservation state analysis was performed instead with the support of a quick photogrammetric survey, because we didn't have up-to-date elevation, and so we had to cope with the lack of material by doing this photogrammetric survey that was really useful to have this base layer on which report our studies on the surfaces. And here we can see the table, the facades of the building with this kind of general analysis without any in-depth study, because we didn't need it. So we are talking about an energy and environmental improvement intervention. It's not and obviously we have to get a general idea also linked to what we are going to do. But still, if we would have found like really big problems on the conservation head, we had to go deeper also in this kind of analysis, obviously. Based on all these analysis and the documentation gathered, we developed the first hypothesis of homogeneous wall stratigraphies that were subsequently checked with infrared thermography survey. And this was mainly needed to define building stratigraphies and to highlight typologies to be measured with heat flux meter analysis to get the numbers we needed to do the simulation. And this kind of analysis proved really useful because it allowed us to understand a lot more than just the measurement points for the heat flux meter. For example, we were able to spot different construction system between the second and the third floor that we had hypothesized, but we were not sure about that from the geometric survey and the architectural analysis. We were able to tell differences in the roofing system in the floor of in the flooring of the third floor roof, because it was a recent intervention and had different techniques. And also we were able to spot some difference in wall stratigraphy and thermal behavior between two different walls that seemed continuous. So it was also something that we could not tell from the geometry and just looking at the building, but was highlighted by this kind of analysis. And it was also useful to have an idea of the general crack and infiltration situation of our windows that were almost entirely new. They were not that old. It was, but they had a lot of infiltration problem nevertheless, especially not on the window system, but on the junction between the window system and the wall. And so, for example, this is a schema that we used to track heat flux meter measurement points. We created a matrix of the elevation of the buildings, and then we defined the homogeneous stratigraphy, and then to define the number of measurement points that we needed to characterize the building, and thus because we also had obviously some cost and time constraints, we needed to do it quick. So heat flux meter experts asked us to optimize the selection of the measurement points. They gave us some criteria, like we need to have really low solar radiation, and so we performed a sunshine hour analysis on the building on the exact month of measurement that we had for this analysis, and then we updated the metrics of the facades of the buildings, trying to find the best section of the building to measure each homogeneous stratigraphy of the building, and this helped us going smoothly and finding the best points for these measurements. And also on the inside, we used infrared thermographies to position the measurement points, because you can never know if you're pointing, if you're maybe just 10 centimeters in the wrong way and you are over something that is completely not the wall, something different, and so yeah, a pipe or something. And so this was really important. The points were left to measure on average 3 to 4 days, because in Italy we have regulation on the measurement points. But however, and before changing the measurement points, we collected the data, we checked the stabilization of the curve representing conductivity. However, this is an historical buildings, and you cannot take anything for granted. And so, due to these massive walls, and despite all the precaution used, the data collected required further verification that we carried out with a kind of inverse dynamic simulation of the wall elements that had as input part of the data collected by the heat flux instrument. And this allowed us to also to cut some strange measurement points, to check again some other measurement with the other analysis, and in the end we were able to tell with a good degree of accuracy, because over the different parts of the buildings we get consistent values of the same materials behind that walls with that thicknesses, and so we were able to tell two main typology of historical masonries and a recent non-load bearing masonry in the third floor. And in parallel, we started also the indoor environmental monitoring to support both input data for the energy model and further calibration with the room temperature. And the results showed a very, very, very stable trend in building temperature, with less than 2 degrees of daily temperature range in winter and summer, which also led us to further investigate the HVAC system settings and to discover that due to an undersizing of the generator, they were on 24 hours a day to keep that temperature. This was quite a surprise for all of us. And with the point cloud of the building ready and the model element table, so a document that defines properties to be inputted in the BIM model for the use of building performance simulation, we started the interoperability activities that Letizia was talking about some time ago, and they were divided in the phases that we have already seen. We also involved the software developer of the energy simulation software. And in the first phase, we started easy with boxes, and just to check general interoperability problems on general issues. Then we progressed to a part of the building that was representative of all case study specific issue that we were capable to anticipate. For example, the height differences among the same floors. That is something that is kind of complex to deal with in building performance simulation. Sloped roofs, large amount of windows, really complex windows with a lot of differences in the inlets, in the boxes, in how in the frame, and also ceilings and walls. And by the end of the second step, we developed a protocol, manual to guide the modeling from the BIM model to the building performance simulation software. And adding also parameters for the translator from BIM to IFC, and this was designed to this guide, this manual that was also embedded in the general project guideline, was designed to allow experts involved to be able to study the entire process or just their part and just follow the rules to streamline the process and to avoid the errors that we were aware of. And the last part was the development, the modeling of the whole building in BIM and the transfer in IFC, and then within the building performance simulation software. And we see in the picture in the bottom left that there are a lot of problems still to be dealt with, but that they are all problems that we know of, and so in the part of the guideline of the manual for the simulation expert, you know what to do, you know what to check for, and then you can work in solving the issue that we know are within the model. In this quick video, you see the whole process. Once imported the model into Thermolog, that is the simulation software from ArchiCAD, after a post-processing phase, we arrived at the final geometric model that you see in here with its definitive stratigraphies. The thermal zones were modeling according to the European regulation for the simplified dynamic calculation 52016, which imposes particular constraints. And then we finished the model with the system, and we started the calibration process with the energy bills and with the indoor monitoring and tailored weather file acquired from a nearby weather station. And country-specific requirements like humidity checks or thermal bridges that were mostly due to geometry were calculated according to the Italian regulation, the latter with finite element modeling. And this is what it looked like, the finalized anti-opera model at the end of the whole process. To overcome the problems related to the collection of data on the use of the building that was very variable in itself and which has become increasingly randomic during the COVID-19 period of lockdown and whatsoever, the monitoring of the target rooms was used through the elaboration of profiles of typical seasonal days for the definition of the thermal set points of the simulation and to support the identification of the thermal zones. Thermal zones that were defined thinking also to the design phase, so we had to keep separated the service spaces like toilets and hallways and staircases, or for example corridors from offices, just to be flexible when doing the design, when designing the intervention. We post-processed the energy bills to get the monthly and annual consumption, and then thanks to the specific type of contracts, we were also able to identify daily from night and unoccupied consumption. and the average energy consumption, excluding heating or cooling, like lighting equipment, elevators, was investigated during the free-running months, such as May and October. To tune the simulation energy consumption to the energy bills, we used the indoor environmental monitoring of key rooms as a calibration reference, and this proved extremely useful and allowed us to find also some hidden errors in the initial simulation inputs or in our assumption on the model. So, like system set points and the usage schedules that we were talking earlier. And some tweaks to the simulation also were needed to deal with some ISO 52016 regulation limitation that impacted our calculation due to the size and complexity of the historical case study building. For example, in this regulation, one simplification is that thermal zones do not exchange heat among each other, and so we had to find some mean to instruct the simulation to take into account thermal zones that, for example, had no systems, but nevertheless had an impact on the surrounding thermal zones. And so we had to also think out of the box, also with the developer of the software, to overcome these problems. And the whole process then allowed us to move from the validated building performance simulation model to the simulation-based design phase, which led to the development of 3 progressive intervention scenarios, including passive, active, and renewable energy sources solution with their related energy consumption reduction. But this is obviously another story, so we will not be going into this part, but obviously you can find the information on the website of BIP project, BIM for energy efficiency in the public sector, and on the website of our laboratory, and you find also the link in this slide and the QR code. I think that that is all.
Thank you very much.
Thank you very much.
We hope you enjoyed.
We hope you enjoyed, and see you and have fun with the course. Bye bye.